Okay, so before starting, let's say what are the program for the rest of the course. Just to know. So now we finished this uniform integrability and tightness. And essentially these are two concepts which they are very useful. They allow to have an extension of the Lebesgue dominated convergent theorem. But actually you see that this is just, this is my feeling. Well, it's a nice result, but actually it depends only on what I know earlier. So the basic tools is always that you can control, well, in sets of finite measure, essentially you need to control smaller sets, and then for set where the set have infinite measure, you need to control the tails. And if you look at all the results we have, essentially, you have, they depend on this control. And because once you are in a set of finite measure, you have Egorov or losing. But losing holds also infinite measures, but actually, essentially, in finite measure, you have the best results you can hope, and so the rest is to control the tails. And if you think also the Lebesgue measure is always the same trick, no? Because of the measure of a set being countably additive is the measure of pieces which are finite. And this holds in any space, so that the measure we have this property, they are called sigma finite, so they are a countable sum of pieces where they are finite. So after this thing, then we see another notion of convergence, which well, is important because the idea of all these theories is that you can prove results which in classical analysis are easy, in some sense, in a much weaker setting by always removing sets of small measures. That's the idea. So the next result is the convergence measure, where you don't have the convergence in like the integral. So all the theorem we have so far is that the integral of fn converges to the integral of f. If fn converges to f, then plus something. Okay, now the idea is that instead of saying that fn converges to f pointwise or almost everywhere, which means essentially pointwise, because on the set of measures 0, we can redefine both to be 0, for example. So you say that they converge up to a set of arbitrarily small measures. You see, the philosophy is always the same, no? I replace something with the same thing by removing a small set, on a set which is slightly smaller. And this is the convergence measure. And then basically we finish the measure theory for the Lebesgue measure, and now we have to decide what to do, in some sense. Because at this point we can either decide to do the general case for measure, for example, in RD, the Lebesgue measure in RD, or measures in general, or we can, unfortunately, I have to cover another thing, which is the fundamental theorem of calculus. So this is something that, well, when in classical theory they introduce the integral, and then it is the inverse of the derivation. No, so the integral is the integral of the derivative is the function plus a constant. Okay, so how this works in a weaker setting? Well, this becomes a little bit more complicated. And so this leads to an important class of, two important class of functions, which is BV function, bounded variation, and absolutely continuous. So I think they are more important than the general measure theory. The general measure theory, last year I did not arrive to do the proof for general measure theory. So at some point I need just to tell you the statements, because you need to know them, but the proof they are personal. Since I'm slowing down now, I think we are in the same problem, in the same situation. So at the end, I need the 3 lectures for differentiation, and then we are left with 2. And I think we see just the theorem, and the last one will be about examples of exams for. I hope to do something better, but really, it's in 22 hours, it's impossible. Okay, so let's do this theorem. So So what we want the goal here, so extend Lebesgue theorem. And what you can see as an exercise. Indeed, everything, it is my feeling, everything is an exercise once you know the basic tools. The basic tools are the three regularity principles, remember. And if you go back there, everything is based on the sigma DTVT. Okay, so let's see right here the Lebesgue theorem. So now we have Fn converges to F almost everywhere. And we have that Fn is less or equal than G, and G is in L1. Then the integral of Fn converges to the integral of G, or yes, of F. Actually, let's see an exercise here. So is it true? Prove which seems stronger, no? Under the same assumption. Seems stronger.
Also, Fn converges almost everywhere to F.
This converges to 0.
The same setting, yes. This one converges to 0. Sorry, minus F converges to 0. And okay, look at this guy. It's the same theorem. It's just the same theorem. Seems stronger. Okay, so let's move, and here they state that this is the Vitali theorem. I have to confess that I saw that thing only on this book, but because in some sense it's an exercise, but it's a nice theorem. Okay, so I still have to keep this guy, because if they do not converge on a set of positive measures, but clearly the limit cannot be the same. No? And now what I want to replace is this assumption here. You remember, we saw last time that this assumption implies two properties, no? I want to replace that Fn is uniformly integrable. And, well, it means that for all epsilon there exists a delta. For all a measure of a less than delta, for all n, the integral over a of Fn is less than epsilon. And the uniform here means that, well, clearly if I put n outside the existence of the delta, I'm fine. Because if delta depends on n, that's fine. Being integrable, you get that when essentially you cut the parts where f is too large and the integral is small on that part. And then when f is bounded, you can cut it. But this does not control the tail. So the tail of the function when x goes to infinity must be controlled. Otherwise, I let the mass to escape in these directions. And sorry, I have a problem. Sì, pronto? Sì.
She was here.
Just look cozy and just the reasons that I'm talking. And the video on YouTube with someone will change and find the professor going out.
Your sound is also recording. Your sound is also recording.
So, and the condition that you control the taste was called the tightness. Which means now, so tightness means that if I only take sets which are very far from, let's say, any bounded set, from a bounded set, a large bounded set, let me say, then the integration there is very small. Okay, so here, so the statement, let's find the statement which is for any space. So for all epsilon, there exists K compact. Now I remember. For all n, the integral over the complement of this compact set is less than epsilon. The conclusion is the same. Okay, so let's do the proof. And we cut essentially a large chunk of the paper, of the textbook. Unfortunately, the position is not the nicest because they're there, so let me put, I just copied this guy here in order to have space. Actually, I should also say that f is in L1 here, no? Because it's not clear a priori. Before was clear because f, so before, let me put it here. If fn less or equal than g in L1, and fn converges to f almost everywhere, then f is in L1. That's triggered because essentially you pass to the limit, and the absolute value is a continuous function. So pointwise you pass to the limit, you have that f is less or equal than g almost everywhere, which means it is in L1. But here is not clear, no? Because the limit maybe can blow up by any reason. But let's say it does not go up. So part of the statement is that you have that the integral is fine, but actually, okay, I wrote something.
But doesn't saying that the integral of fn converges to the integral of f implies implicitly that f is integrable?
It can be plus infinity.
So you say here that the integral of f is also finite.
Yeah, it can be a positive function, so you have the definition when this is plus infinity, and then your integral it goes up, no? But actually, okay. So let me so I know this is very bad for lecture. No, it depends how you feel it. I prefer that. It comes to, in some sense, I prefer, I write down what I want to talk, more or less, and then I change when I'm here, because, well, slightly change, because I see something that seems nice. So one of the doubts here is that I can prove the same statement. So that the integral of fn minus f tends to 0. Is that true or not? It depends on the statement. Because I want to understand the following. Is this addition here a significant one, or is just as before? I mean, if you have this guy, well, you believe that it's not possible, more or less, that f is in L1. No? Because these guys, we will see they are in L1 essentially, and so it cannot be. One has finite integral, the other cannot have plus infinity integral. And then you have a convergence. The distance will always be infinity.
Clearly this is big above the absolute value, but I'm not sure we can integrate f.
Yeah, that's the problem. So it's really an important addition here.
Sorry, why could this not be convergent to 0?
Okay, we have that fn converges to 0. Fn minus f converges to 0.
Yes.
But the problem is that the tightness and the integrability. We don't know it yet, simply because we know just for fn, while before we have g. Understand what is the problem?
This fn minus f model is smaller than 2 epsilon. Maybe it's uniform integrability is same. It's smaller than 2 epsilon.
What is integral?
I think that's what.
I
So,
think he's saying that
if this integral is less than epsilon,
Yes.
but this will multiply by the measure and the measure could be infinity, so
Yes, smaller than epsilon delta.
so I have to write like this. That's something like no? So that it is true. So this means that so if you have this goes to 0, and f is tight. And let's do well, you see the same is for the case that uniform integrability, no? So if this is less than epsilon, then you have the integral over a
but how do we get the bound of epsilon? Because we want to prove that the integral converges to 0. We only know that fn converges to f almost everywhere. So how do you get that the integral of the modulus of f minus fn?
yeah. If we know that it is converging, then it is tight. So we have to prove actually the following result. Let's say integrable tight, then integrable and the tight. Yeah. But actually, it's not saying that if you have almost everywhere convergence, then this holds, no? Okay, so let's try with the theorem. So this says that the addition is not a trivial one. It's non-trivial. Okay, so how to approach this theorem?
We take a sequence of bound functions converging to Fn for every n, because we have nothing to do except with the approximations for
Yeah, let's
by
do the
bound
thing.
function.
Yeah, let's do the thing. So define, let's say f k n is equal to f restricted to k. So this means that it is f if f less or equal than k, k is f larger than k, minus k is f is less than k. This notion, no? This notation. Then integral of fk ma fkn. So okay, so now we know that by uniform integrability so the measure where modulus of fn is larger than k is less than, okay, we can say, let's put in epsilon, then we see epsilon for k sufficiently large.
Excuse me, what do you mean by k if k is greater than k? Here in the definition.
What? If a is greater than k is a value, I cut to the value to k. It's pointless.
Okay. Okay. So
Is a point. So I know that, well, this goes to 0 for, well, because at some point, essentially, I know that this, if this is sufficiently small, the integral in that set is small. So I can take a k sufficiently large such that the area here is very small, and then it means that the integral is smaller than that. Or here I can also take that is even better. So that even better. Let's say, or better is okay. How to deal with that for this guy? Well, for any n, this set is less than delta. So let's put. I just confused, and then like this. And then when it's less than delta, it means that the integral is less than epsilon. So at some point, the k is uniform. Do you agree? Because otherwise I have a set which is very small, and f should be concentrated on that set. So it's very large. So this one was the notion we wanted, no? But actually we wrote it. Okay, so it means from this guy we have then integral of fn is equal to the integral of fn cut to t space plus something which is of order epsilon. Because it's the integral when I cut it plus the integral when it is large, and when integral when it is large is bounded by epsilon. Okay, very good. That's fine for the set where it is large.
yes, we now need the uniform integrability.
Uniform integrability, yes.
I think this is by.
So we need the tightness. This is the uniform integrability, it's here. It's already used, no? Because now we want to use the Lebesgue theorem. We need the tightness. But it's the same, no? Now the same K. The previous restricted to the set minus K. K. Then by tightness the integral for x larger than k of f n, okay, is less than epsilon, which means again that if I restrict this guy to the x less or equal than k, fn is equal to the integral from x less or equal than k, f cut to some k, plus all the rest. So let's make a picture of this thing. So essentially it's something like, I just take this square. And then when I have a function, I just take this function here. So what is left out? But what is left out is this area here, this area here, this area here, this area here. But now the assumptions, uniform integrability tells me that essentially if the region here is very small, then I'm leaving out something which is very small. And this holds uniformly in N. And since I know that, well, for any given f, when I go up to k, the measure is less 1 over k than the integral of n, essentially I have a bound, this means that I'm pretty fine. On the other hand here, the tail is controlled by the tightness, because I know that if k is very large, the integral over there is very small. Okay. So at the end we reach the Lebesgue dominated conversion theorem again. Indeed, we don't have much tools again. So now we can apply the theorem to this guy. So let's do that. Converge to what is this my f, and this is scattered to nk. So this, let's say my, no, this is my f. So it converges to f scattered to k. So modulus x less or equal than k, and well, let's say it is f tilde k, which is f if x less or equal than k and f less or equal than k. Otherwise is minus k, f less or equal than minus k, and x less or equal than k, all the combination k, f greater or equal than k, x less or equal than k, 0, x greater than k. Very well. So I
think you are reversing the n and k, because this is in the rotation mean k in the super.
So what I have that integral of fn plus over of, let's say, minus the integral of this f tilde k. Okay. That thing is converging. So I have the lim sup over n is of order epsilon. So for any epsilon, I have that this object is small. Very well. But now I have a problem because I would like to replace this guy with f. And here I can erase because now we know the two. So I prefer, well, here's a big part. It are two sections that I'm collecting in one truth. But it's just that we need to construct and see which pieces appear. So we have a trouble here. If we know that this is in L1, then we can pass to the limit.
If we know that f tilde
Is in L1, no, f is in L1, then we pass to the limit. So we need to prove that actually this is really the case. So the limit of f is in L1. So do you agree, no? Now we have only that if I cut, the difference in the integral is small. Okay, how to do that?
L1 means that it is Lebesgue integrable and
It's finite, the integral.
and what?
The integral is finite. The absolute
The integral of the modulus is fine.
Do we assume that if n's themselves are in L1?
Okay, yeah, let's do this. Yeah, we assume they are in L1. So let's put this something here. Here I need to add, but let we discuss this. But they are in L1.
Ego, I've already
Well, you don't need just that. We need to think if that object is today is a little bit funny. If that object converges or not.
It must converge. Fn, k, it's converge.
Yeah, it's converging, but
Also the integral
maybe
because-
it goes.
But
Fixing k,
if
If
it
it
doesn't
converge,
converge, then it means that there is some bounded functions below f that the supremum over the integral would be infinity, right?
Yeah. Okay, let's do an example. So let's take Fn is equal to 1 over n, the indicator function from n to n. So 2, let's say, because from n to 2n, but then I have n plus 1, so it's 2 to the n, 2 to the n plus 1, and I divide it by 2 to the n, 2 to the minus 1. Actually, this does not lie. I don't like it because then the tails is always 1. So let me put divided by n. Okay, is that uniformly integrable?
No, because at 0, the function is like this. Like a step function, but increasing, right?
No,
No, actually, I think
it's
it's
the opposite.
decreasing.
It's decreasing.
Uh,
To the minus n of 1. So yes, it's bounded. So it's Fn type.
yes.
Yeah, it's type. Well, the limit is 0. And indeed, actually, the interval of Fn converges to 0. Because I don't want to look now, I forgot how to handle the tails, I'm sorry. But I don't want to look at the thing, because I changed already a lot of this. So let's see. I think I have to look, because I forgot.
I thought that if we fix it k, we can say that if k in the limit of n is L1, so maybe we can take after that the limit.
If we fix k,
Fix, yes.
yeah, this is in L1 for fixed k, yes.
We can after that we cannot. No.
I don't see what you want to say. So, if for fixed k that's in L1, and then you know that this is close to this limit, but then
It doesn't prove.
this is because I tried, but because if you don't know, you maybe try, and then you see what happened. How it happened here that you have something positive, so you don't have cancellation, but it works. So maybe the trick is to consider something positive. Well, let's do that. So, I'm sorry, I really prefer it this way. I know, but for somebody of you, maybe you're not used to, well, you are used to something that presents something perfect. But when you work, is not, nothing is perfect. So actually, you have to approach and get an idea. So here, the idea, I believe, is the fact that take now Gn equal to modulus of Fn. And let's do the same. So Gn clearly converges, but the modulus, the absolute value is continuous to G, which is the modulus of F. Okay, so let's do the same. From this one, I have the statement that dim sup the integral of Gn minus the integral of G, and now, well, it's G tilde K, less or equal than epsilon. And now something comes to my mind. That's G. This is cut to minus K, K, and K. What it comes to your mind?
Compare it with the area of the
When K enlarges, this converges to the integral. So
yes,
what is
yes.
the difference? It is subtle, but what is the difference? Is that here, this F tilde has a sign. I'm in trouble to give the integral because I must first prove that the positive and the negative part have finite integral, and then I sum. Here I don't care. Remember, but monotone convergence. The integral of g tilde k converges to the integral of g. And that meant I saved the day. And now, can you finish the proof? Just you can say, well, yes, I use some ketchup and then it should work because McDonald's is the best mathematician. But well, I want just a puzzle. You see what is the
Just here that because of this that you say that the integral we want converges to the area of the rectangle when k is big enough, right?
But we proved just on the model upside coordinate and not just to.
It means that we can compute the modulus of the integral of f compared with the integral of g. No?
the modulus of the integral. Well, actually,
yes, that's. It means that
we just
f
take
is-
f. Just take f and g and gn now.
Okay.
Okay, so let's come back to this object. Or this object, which is the same. So from this, well, or the computation, I know that you have to finish. You have this plus the integral of g tilde k n minus, so that's it, everything is cut. G n minus g tilde k n is less than 2 epsilon. I cut this set, which is epsilon, and this set, which is epsilon. This is uniform. Plus, this guy tells me that the integral of g tilde k, essentially this tilde k converges to the integral of g tilde k. And the proof. Okay, so I have. Okay, let's do by contradiction. And then stop me whenever you see the end. Assume that the integral of g is plus infinity. What I get now? This is as large as I want.
So this also becomes as large as we want. So also g k also become as large as we want.
But
But it's bounded by this.
2k squared. Okay. Can anybody of you repeat the argument here? But you finished by so essentially, yes, I can prove that thing. But then I discover I have a problem with knowing that f tilde k converges to the integral of f, which is fine if f is in L1. Okay, then well, either you don't need the example, but actually if you don't have it, you try with an example to see what happens. And then I saw with the positives that I cannot do anything. I was locked. Why I was locked? Because for positive I have the monotone convergence. So this object I don't care if it is plus infinity or finite. It works by approximation. Oh, so if this is too large, this is too large, this is too large, and this is very large, but actually this is cut, so it is k squared. So essentially I deduce that this cannot be plus infinity. This is in L1, and I'm so happy that it's whole. Then from the proof I deduced this exercise, which I can put earlier. Indeed, in the book is at the beginning. You start by proving this object. Then we discovered during the proof that this is the case. So why?
Exactly because of this discussion.
Exactly. Because of the discussion. I cut at some point that this is the integral in this set is small because the set becomes small because f is a real value. So at some point, almost every point has a bounded value. And so the integral here is small, the area here is small, and the rest is k-squared. 2k-squared. Okay? And I save the data. Okay, so let's do something a little bit more. So the uniform tightness and the uniform integrability, the tightness and uniform integrability is meaningful for, so from clearly the opposite whole, no? It's trivial, the opposite whole. So the following, if f n is a finite family of functions in L1, then, so let's call this f. F is uniformly integrable and tight. Ideas here? Okay, let's do. For some reason, it's easier to think about the tightness. So in some sense, it's the opposite of what we have in the theorem, but only for finite families. Usually for countably many, it's already false. We have the example of translating interval.
What's the example again for countable?
For countable, we just take the translating interval. That's clearly each function is in L1 but cannot be tight. And vice versa, you can move something going to plus infinity and still it's.
Yes.
Okay, so how to do that? Let's start with the tightness. So for each f, for each, let's say, n, and for each epsilon, for each n, there exists, let's say, a constant k, which depends on epsilon and n. The integral from x to the isolation of k epsilon n, fn is less than epsilon. What I do now?
I think if we start with epsilon, we take epsilon over n and do this, and we get this n case. And then we take the greatest.
Yeah, but why you need to replace epsilon? You're not summing.
Ah, okay. Yeah, so I think
But it's
that's-
yeah. So the fine. Tightness. Sorry. uniform integrability. What I know is that for all epsilon, for all k, for all f, for all n, there exists a constant k which depends on epsilon and n, the integral for, let's say, I can write something else, something like, okay, the tightness means that there exists a delta which depends on epsilon and n. If the measure of A is less than delta epsilon n, then the integral over A over n is less than epsilon. This is the definition. And then to prove that are essentially uniformly bounded,
You also take the maximum? The maximum of the delta?
the minimum, the smallest one.
Yes.
Okay. So now let's go. Let's extend. I need to a little bit. Well, this was already a little bit. Because inside the theorem, inside the proofs, there are several results. No. But you understand why you need the results. Because I want to prove the theorem. And then I have these pieces. And the pieces come up naturally because you discover you want to prove something, then you need a piece, and then you do something else, and then finally you understand that there are all these pieces inside. So the fact that you have finitely many, you have this guy, candidly many, is the fact that this holds everywhere. And this is the basic notation, the basic observation. If I know uniform integrability and tightness, I'm certainly in L1. Okay, so now we change and we go to the convergence measure, which is still the idea to replace the almost everywhere convergence with something weaker, because sometimes maybe it's not sufficient. Okay, so the idea, let me put the idea. So now we want to replace okay. What does this imply? Use several times. Then so I know that, well, the set where f is larger than delta converges to the empty set, or to a set of measure 0. Because the union of the complement is growing to the whole set. So in bounded sets, because I need to use, well, if you remember, the intersection of set of the measure of the intersection is the limit of the measure only if one, the first, let's say, is finite measure. So in bounded sets, this is okay. Okay, so I replace this guy with that assumption. So one implies the other. Then now I want to discover if the other, which sometimes is easier to prove, implies the first. With the measure where fn minus f is larger than delta tends to 0 for all delta greater than 0, not from delta equal to 0. So this assumption here is the convergence in measure. So let's explore immediately if the opposite holds. So exercise. Find Fn converging to F in measure. So let's see, the problem can be unbounded sets or bounded sets, but actually since I want to prove almost everywhere convergence, it's like in bounded sets. But
I think you just mistyped with the find the. You want the convergence in measure condition, not the convergence of Fn to F, right?
yeah, this is the notion is it means this one.
Okay.
When I say Fn converges to F in measure, then I'm this guy.
Want to explore when it implies limit one?
Yeah, it does not converge almost everywhere. But here we have the example does not converge in L1, but it converges almost. The example we have is something which converges almost everywhere. Okay, so let's do. Okay, so let's do something like this. This is the first. This is the second. This is the third. Let's say this is 1/2. And then I just translate. Then I take something even smaller.
Sorry, what is the Grom's function exactly? Half the interval or?
Okay, I don't want to write down. I just want you to understand, to see by yourself. So let's see. So what it requires is just that the set where they are very different is going to 0.
Yeah.
But this set has more measure, but is not saying where it lies. So I can put wherever I want. So it's different from this implication. This implication, these sets are shrinking.
Yes.
So I can apply the monotonicity of the measure.
Yes.
But here, I'm not saying the position of the set, just the measure. So I can imagine that even if the set is very small, like a small interval, I just move at any n. You see? And it means that for any x, at some point, there is an n whose difference is 1. So it's not converging. Then I take something even smaller, for example, half. Doesn't matter. I just need twice the number of steps, and the same x at some index will be, the difference will be 1. You understand? You don't understand.
I understand the general
Idea.
but not the example.
Okay, so let's do the example then. So define f, let's say 2 to the, so fk is equal to k plus 1, 2 to the minus n, when k is between 2 to the n minus 1, 2 to the n.
Excuse me, what do you mean by fk equals number multiplied by interval?
This means that the indicator function
Okay.
is equal to 1 in k plus 1 whenever k is this index. So give me a k, I find n such that it lives in one of these intervals, and then I put this value here. So how is the function? So let's fix n, which is one interval. So k leaves from 2, n minus 1 to 2n. So this guy, what I get that the value leaves from 1/2. The first is 1/2, whose size is 2 minus n. And when I go to the end is 1, 2 minus n. And I jump off sizes. So each k translate the function of step 2 minus n. It's just the thing. Give me k, I find an interval, and then I can put which of these. So the function is something whose size is of the order logarithm of k, or this index n, and then the position is decided by k. Now give me any x, which is known in the boundaries, but I can. So let's say let's close it just to be sure that we take by default. Give me an x. From this definition, fk of x is equal to 0 or 1, but depending on k. So for some k different than k bar, and k equal to k bar, which depends on x. Because at some point, these intervals contains x. Okay, so this function, you see, for any, no matter how large is the index k, at some point I take the value 1, and at some other point I take the value 0. So it's not convergent. Do you agree? So even k is extremely large, it tells me only that the set is very small. But since I pass all the points in the same interval, at some point will be 1 for any x in, let's say, 1/2, 1. And now, is this fk converging in measure to 0?
Yes, it's becoming small.
Yes, because fk well, from that definition is when k is less than greater or equal than 2 n minus 1 goes to 0. Conclusion. Does not imply almost correct. But I can make an observation here.
Maybe polygons less.
Point-wise, no, but
Almost similarly, that's
almost yes. That was the observation here. Okay, but in bounded sets. And then let me ask, if Fn uniformly integrable, let's say just tight.
But isn't 0 a bounded set? And it is not true here?
Pardon?
You say that convergence in measure doesn't imply convergence except in bounded sets. It implies it, right?
The convergence almost everywhere implies convergence in
okay.
measure. The opposite true in bounded set. Let's say just instead of losing for in uniform integrability, then I'm fine because I can also replace bounded sets, no? So then is true in R. Because remember, we have the lemma or the proposition which says that in this case, the integral of a decreasing family of sets is equal to the integral of the intersection. Remember, because we saw several in different ways, no? Because f and the integral of fn is like a measure, or g is like a measure which is finite, or you can just do it by exercise. Okay, but let's come back to the example and see what I can say a little bit more. And then it's the end. Well, it's something like compact sets. If I have a sequence in a compact set, I'm not saying that the sequence is convergent, but a subsequence may be convergent. So is that the case here? You see a subsequence which is converging?
Converging, I mean, almost everywhere? Or?
Sequence which converges. So I take a subsequence of this sequence,
Yes.
which converges now almost everywhere. So I want to state that if converges in measure, then it converges almost everywhere for a subsequence.
Risk theorem. Risk theorem is, I mean,
Ritz theorem?
Risk theorem.
Which one?
No, this is a Risk theorem.
The name.
Yes.
Okay. Well, I don't know. I think I it's Ritz theorem. Maybe yes, it's not. So, which is the subsequence? How we can choose the subsequence in this example? So the problem is that these sets are translating, no? So they span all the interval. But at some point they have to come back. So if once they are back, I just take the points f k with k equal to 2 to the n. What is the n? F2 to the n is equal to the indicator function of, if I'm, okay, I need to close it, sorry, otherwise I jump a point. To the n, so it is 1 plus 2 to the minus n. And now this is definitely converging almost everywhere. Actually converging everywhere. Okay, so I arrive to what is the possible statement. However, there is something here which a little bit disturbs me. And then I ask you. So clearly, if Fn converges to Fn, if the statements hold, it means that the limit in measure is unique. Because this is a standard limit. It's unique, yeah, because if it converges almost everywhere, so for any point it converges in the sense of R, and the limit is unique in the metric space. But here I'm not saying it's just a definition, I'm not giving any topology to that object, no? I'm not saying that it is there is a topology or a separable topology so the limit is unique. So I face the following question. they have two limits. Is the limit unique? Because I'm not constructing the topology and then I'm fine. It's just a definition of an object. If you give me f, I check whether or not it converges in measure. While here, I know that if you give me fn and it converges almost everywhere, I can construct what is f. I fix x and I take the limit. So the limit exists for almost every x by definition. So this limit is perfectly defined by this guy.
But it could be that there are two different subsequences. One converges to some f's, the other converges to some other g.
But then you mix the two, and then you take, yeah, it could be, yes. Yeah, it could be. That you have two different subsequences.
So the answer one would expect it is no.
So yeah, it could be no, that you have two different fg. Indeed, this is the problem that I face, no? When I read the theorem, I have what I mean. I have some trouble here. Well, if you have two different subsequences, you take the sequence f converging to g, while here it converges to f. I think you cannot match it. The theorem would be false. Because you see the f is the same. If this has 2, that has 2. But it cannot be. Two different subsequences, but then the subsequence that you use here, you place here, converges to G, and then the piece converges to G. It sounds, cannot be left. So that thing should be true. How to prove that?
We take the intersection of the two sets where they disagree.
So if converges to G also. So let's say minus plus f, so let's say like this, f minus G, fn minus G plus fn minus f. And then you see that if this is different from 0 on a set of measure greater than 0, at least one of the two is larger than 1/2 on a set of the same set. So contradiction. So this is the measure of fn minus g larger than epsilon half. The union the fn minus f larger than epsilon half should be larger than the measure f minus g is larger than epsilon. And then it cannot converge in measure and have two different things. Oh, and then it's something relaxing. I know that when you understand, but yes, it should be relaxing. I tell you that if you know that fn converging measure, then this object is defined. Can be something else. Okay, so let's go. So let's go, and essentially the leading thing is that example, no? That before doing formally and so the trick is always to reduce the theorem to something and essentially to that example. Not in the sense that f is the same, but in the sense that I see which sequence to choose.
Without anything else, just convergence in measure?
But I'm not saying anything about f. It's measurable certainly, but I don't say any integrability property. Well, before we have the integrability property here, well. Okay, so and actually let's cut down to bounded set. And the statement holds in here. Then the statement holds in. So then I can replace the converging measure in each bounded set. How to do that? This is standard. So it means that for any n, okay, this is sorry k because it's not the same as n. For any k, there exists a subsequence f of nj, which converges to f almost everywhere in k plus 1. Now,
we restrict f to these intervals.
yeah. It means exactly the string is the interval. Now,
And now we apply the theorem for in these bounded intervals.
yeah, and then I have this statement. So let's. This is a diagonalization. You know the diagonalization process.
Yes.
Let's see. So let's say in 0, 1, I extract the first sequence. Let's say nj, and let's say nj1. But this is converging in measure also in the other, because it's a subsequence of something converging in measure. So now I extract in 1, 2, I extract the subsequent, let's say, or in -2, 2, doesn't matter, but 1, 2. I extract the subsequence. F is a subsequence of this sequence. No?
Yes, yes.
So it is n1, 2, j. So at the end I have, well, you know the picture, no? Here I have the k, well, all the k's, from 1, -1, 2, -2, and so on. And here I have the index n. So here the first one, the second one is a subset of this guy. The third one is a subset, and I have all the
If we do
subsets.
this subtraction infinitely countable many times, it could result in empty.
No, why? You take the first, here you consider you don't change the 2, you change the third, then you take the diagonal. The diagonal is that always, no one is empty. And this one is always, well, this one is offset of this one. And so it means that for any k it converges. So this is the diagonalization process. So we are fine. And then you see, already we are in the setting where we are in the bounded circle. Now, let's be a little bit smarter in this example. So I will erase this thing. Okay, because the example has something which is nice because I see it, but I have a lot of controls. So let's assume, for example, that I know that fk, so I can also observe the following. So the measure when this f to n is different than 0 is less than 2n is equal to 2 to the n minus n. So the sum, so now I know that each one is a subset of the other, but I can also say that the sum from n to plus infinity of this measure is less than, well, is equal, less than 2 to the minus n plus 1. Fk, f2 to the n. And even if I don't know the position, certainly the set has finite measure. So at some point it's definitely 0 on a set of large measure. So what I gained before, here I don't need to care about the position. I'm just using the fact that these sets, the measure of these sets converge to 0. So let's do here. So for all epsilon, in a bounded set, no? Because I can, the trick is that I need to show that it goes to 0, the measure. So that essentially the rest cover, or, well, we are in a bounded set, I don't need to say. So you can just automatically. Minus f larger than this eta, which is some eta that I define, is less than 2 to the minus, well, okay, here the notion is better, j 2 to the minus j. This I can do. And then we put epsilon. Are you fine with this fact? So just look at the example. The example tells me that at some point these measures are very small. So even if I don't know which position they are, the sum of the measure is uniformly small. I want to repeat the thing. Okay, I take n very large so that this measure is uniformly small, and I define this index there. Now, the sum for n greater or equal than n from j, then n of f of these sets. So let's say, let me put here. Now I want the measure where of the union from j greater or equal than some capital N of the set where f and j minus f is larger than eta. So the meaning of this set is the set that in the future, at some point you have a value which is larger than eta. The complement of these sets are all the x such that they are definitely less than eta. So what is the complement? I take the union of this set for n onward. Let's say this is the set. If x is inside here, there exists a future index such that the difference is large. In the opposite, from that index onward, it is small. Okay? So let's compute this set. It's less than the sum, and from this guy is less than, okay, of this object. And this is less than, if you sum up, is epsilon minus n plus 1. Very small. So I proved that here is, yes, for all epsilon, there exists a subsequence. Well, actually, I fixed the subsequence. So for all eta fixed, there exists a subsequence such that f and j minus f is less than eta definitely, which means from nj very large, for almost every x. So that's because take a set, remove as an arbitrarily small set, which is given by this guy, then for n larger than exactly this n, the difference in the complement is less than eta, less or equal than eta. You see how to conclude?
This set contains possible hidden convergence.
So let's see. I proved that for any eta, for almost every x, I have a subsequence which holds for almost every x, such that this goes to 0. Whatever the lim sup limit of that subsequence is near f uniform. Then it's again what we did before. For take eta going to 0, a sequence of eta going to 0.
Yes.
Because so conclusion, and now I put all the ingredients together. Take eta equal to 2 to the minus I. So for I equal to 1, I have a first sequence. And this sequence, it means that for the first sequence, f for all, so almost every x, f and j minus f is less than 1. Definitely, from some index onward. Okay? Now take I equal to 2. What I do now? I extract a subsequence of this sequence.
But we leave the first one to do the diagonal argument again.
We can, yes. This is a delicate point, but I don't want to tell because there are some details that I believe you can feel, and it's always nice to think by yourself. Yeah, I'm cheating a little bit, but I'll say what. So I start from the first another sequence for which the same hold, and now here I have 1/2. So let's say n1, n2, 2, n2, n3, sorry, n1, 1 is, yeah, I need to have some indexes, n2, 2, n3, 3, and so on. And here I get that f and jj minus f is less or equal than 1. And so I could go on. And then if I diagonalize, so none of these sequences doing bad stuff. If I diagonalize, I get the result. but I'm cheating a little bit. Where I'm cheating, but you probably feel it a little bit. Where I'm cheating.
Maybe it's not maybe it's not diagonal or some other points, other.
I'm not so sure I'm cheating. The book, actually, I'm not even. The book, he does a little bit more because I can be really safe saying that at some point n1 onward, this measure is less than epsilon 2 to the epsilon half. And then I extract the second from this guy. Indeed, I'm not so sure. So how the book solves the problem? I'm not so sure. I think probably it works even without. So it says the following. From this condition, you fix an index sufficiently large such that the set where this does not hold has measure less than epsilon. Now you keep the same and extract from this one something for the second. So essentially, it's like the example. You remove epsilon half here, and here you know that from n larger than n1, it's okay. Less than 2 to the minus 1/2 here. Now in this set, you extract from the sequence larger than n1 a second sequence for which the same holds. So here I remove epsilon 4. And here I have that if n is larger than n2 larger than n1, fn minus f is less than 1/4. At the end what I have, I remove a set whose measure is epsilon, and here I know that if n is larger than some nj, fn minus f is less than 2 to the minus j. Sorry, I'm a little bit going on. And now I want you to think, I'm doing something more. What I'm doing here?
I think you are not taking the diagonal, you are just taking some parts of the diagonal.
And indeed, what I do, a growth theorem.
Sorry?
Takeoff theorem.
Improve Takeoff theorem?
I remove a set of epsilon. For each delta, I find an index n such that the difference is less than delta for any n larger than this capital N. So you see that at the end, the tools are always that. I'm not really exiting too much. It's just it's really like chess. You have only finitely many moves, but you have to make a strategy. Okay, I'm sorry. I went a little bit beyond, but there are some exercises I didn't have time. But actually, all the proofs here are exercises. No? We have to think how to approach the proof. I'm not following the book at all. Okay? So see you tomorrow. Now we have the tutorial.
Tutorial is tomorrow?
Now it seems so.
Yes.